This video covers 2.8, solving linear inequalities in one variable. Objective 3, solve linear inequalities using properties of inequalities. We have seen already with linear equations in the form ax plus b equals c. We would get all of our equations of that form and solve them by subtracting 3 and dividing by 2. Every time we got them in the form ax plus b equals c, we would subtract b and then divide by a. We apply the same procedures with linear inequalities. The first property we use is the addition property. It says for any real numbers a, b, and c, you can add c to both sides of the inequality. If a is less than b, you can add c to both sides. If a is greater than b, you can add c to both sides. Nothing new. So if I have negative 2x plus 3 is less than 7 minus 3x, my goal is to write it in something that looks like ax plus b and c on the right side, except for now the equal sign has an inequality. So I don't want the negative 3x on the right side, so I add 3x to both sides. 3x minus 2x is x, and I have x plus 3 is less than 7. Now we have the plus 3 on the left, so we subtract 3, and we get x is less than 4. That problem involved just the addition property of inequality. Now we express that solution set using set builder notation. That is pretty simple. We just say the set of x such that insert the inequality here. Every time you write set builder notation, it starts with the set of x such that you just put your inequality inside the braces. Interval notation. I like to graph it first before I do the interval notation. So everything less than 4 or to the left of it. Now the interval notation is easy once you see that. The left side of this interval is negative infinity. The right side is 4. We don't include the 4 because it's less than, and we never include the infinity. All right, those are the 3 ways we express the solution set. Set builder, interval notation, and the graph. Now we look at the second part of solving equations, which was the division property of equality, or multiplication property of equality, as we like to say. This one has a little bit of a problem, because if you know 3 is less than 5, if you have a true statement like 3 is less than 5, and you come along and multiply both sides of that inequality by 2, it still says the same thing. It still is true that 6 is less than 10. However, when you start with 3 and 5 and you multiply by negative 2, that's the big deal here, the negative on that, our result is negative 6 and negative 10, but on the number line, negative 10 sits to the left of negative 6. And so negative 6 is actually greater than negative 10. Whereas 6 and 10, 6 is to the left of 10. So when you go to the negative side, the symbol has to flip. So the conclusion is when you multiply or divide by a negative number, you must flip the inequality. And this is a little bit hard to read. It's just saying that if you're multiplying or dividing by a positive number, then the symbol stays as you started with. Less than stays less than, greater than stays greater than. But when you multiply or divide by a negative number, the less than turns into a greater than turns into a less than. This sort of thing arises when your coefficient is negative. To solve negative 5x is less than or equal to 20, you have to divide by negative 5. When you multiply or divide by a negative number, you have to flip the symbol. Greater than or equal to. Now you have x is greater than or equal to negative 4. Graphing that, interval notation, the left number is negative 4, the right it goes to positive infinity. We include the negative 4. The graph is there. Set builder notation, you always write the set of x such that and insert the inequality. Example 4b, when the coefficient of the variable is a negative, we're going to have to multiply or divide by negative, and so we're going to have to flip. We solve this one by multiplying by the reciprocal of negative 4/3. That reciprocal is 3/4 negative. We multiply the other side by a negative 3/4. 3's cancel, 4's cancel, negative, negative's positive. We have p is greater than. 4 goes into 4 once. The negatives cancel. We have 3/5. Three-fifths is equal to 0.6, so we go over to 0.6 on the number line. And it's everything to the right of that, greater than that. And now that I look back, I realize that I had a greater than symbol. And when I multiplied by the negative number, I must flip my greater than and make it a less than. Very easy to forget to flip the symbol, as you see. So it's actually everything to the left of 0.6. So we write this in interval notation. The left is negative infinity, and the right is 0.6. I'd rather use 3/5. Set builder notation is the set of p this time such that p is less than 3/5. Okay, one more time. Because I multiplied both sides of this inequality by a negative, I had to flip my symbol. Adding or subtracting negative numbers doesn't matter. Just multiplying or dividing. Okay, this one, we get rid of the parentheses first and write negative 4x minus 24. Plus 18 is greater than or equal to negative 2x plus 6. We simplify the left-hand side. Negative 4x minus 6 is greater than or equal to negative 2x plus 6. We want to get all the x's on the same side, so we add 2x. And that gives us negative 2x minus 6 is greater than or equal to 6. We add 6 to both sides, and that gives us negative 2x is greater than or equal to 12. It's this step where you ask yourself, am I going to have to flip? And in this case, having a coefficient of negative 2, when I divide both sides by negative 2, I need to flip that symbol over. And that gives me x is less than or equal to negative 6. So I graph this. Everything to the left of -6. Set builder notation is the set of x such that x is less than or equal to -6. Interval notation starts at -infinity and goes over to -6, and we include the -6. And letter D. With the fractions, we want to multiply everything by the reciprocal. In this case, we would like to do it by the LCD. In this case, it's 15. So we'll take 15 times 4/3, 15 times 2/3, 15 times 4/5, and 15 times 3/5. That way we can cancel all of our fractions. And 3 goes into 15. 5 times 4 is 20. 3 goes into 15. 5 times 2 is 10. 5 goes in 15. 3 times 4 is 12. 5 goes in 15. 3 times 3 is 9. I've lost my x. Now we have our fractions cleared. We get all of our x's on the same side by subtracting 12. Now I add 10 to both sides, and I get 19. 8x is less than or equal to 19. Now I see that I don't have a negative, so I divide by a positive, and I get x is less than or equal to 19/8. I don't have to flip anything there because I divided by +8. 19/8 is 2 times 8, 16. That's 2 3/8. Everything to the left of 2 3/8. Set builder notation is the set of x such that x is less than or equal to 2 3/8. Interval notation goes from -infinity to 2 3/8. The last part of section 2.8 deals with, just like equations, we can have inequalities that have no solution or all real numbers as its solution set. We were always on the lookout for things like 2x plus 2 equals 2x plus 3, which was a false statement, and we would say no solution with equations. Or 2x plus 2 equals 2x plus 2 was a true statement, which gave us all real numbers. Same thing for inequalities. If the coefficients of the variable match and you get a true statement, all real numbers. If the coefficients of the variable match and you have a false statement, it's no solution. In letter A, left-hand side is -9x plus 7. The right side is 16 minus 10x plus x. The right side of this, -10x plus x, is -9x. And when we add 9x to both sides, we get 7 is greater than or equal to 16. 7 is actually less than 16, so that's a false statement. This gives us no solution. In B, we have x plus 3x plus 12 greater than or equal to, that's 5 minus 1 is 4x plus 5. The left-hand side is 4x plus 12. The right side is 4x plus 5. Subtracting 4x from both sides gives me 12 is greater than or equal to 5. That is true, so this gives us all real numbers. Now, how do you write those kinds of things in set builder, interval, and graph? The all real numbers case, you would have a graph, and it's all the numbers. Whereas if you graph the solution set to no solution, you just leave the graph empty. In interval notation, you say negative infinity to positive infinity. There really is an interval notation for no solution. You just say it's the empty set. And that really is what you would do for set builder notation as well. But for set builder notation for all real numbers, you'd say the set of x such that x is any real number. This concludes the video for section 2.8, solving linear inequalities in one variable. Objective 3, solve linear inequalities using properties of inequalities.